SQL Azure. So, anybody who's interested, today is session 1. Tomorrow is session 2. If you already know all of this stuff, then you can just go right on to session 2 tomorrow. I think you'll find it interesting. But what we're going to do today is kind of take you through an introductory exercise with SQL Server, do a few demos, and hopefully enlarge your perception of this space. So with that, we'll jump in here. Now, first of all, I'm Ed Catabot. I am the SQL Server Spatial Program Manager. So I was hired actually almost 5 years ago to the day from IBM, where I was, interestingly enough, doing much the same thing on DB2 with the geodetic extender and the spatial extender. Prior to that, I was at Informix. How many people know Informix? Remember Informix? So Informix was my product, Informix Spatial and Data Blades. I did was responsible for some of the engineering on the spatial data blade and the geodetic data blade. So I've got a bit of history here, and what's interesting about that is that this is the third or arguably the fourth time that I've been involved with spatially enabling a relational database. And consequently, I've done things a little bit differently this time. And rather than adding in more complexity, which is my usual modus operandi, I have actually made the product a little bit simpler. So one of the things that we did is we had a few key, let's say, precepts as to what we wanted to accomplish. And the first thing is that the Earth is round and maps are flat. So, it seems rather simple and straightforward, but a lot of other implementations tend to make this not quite so apparent and quite so clear as we've done that, and I'll explain that in a minute. Additionally, it's important to note that SQL Server is not a geographic information system. It is not designed to be. It is designed to be the foundation for one if you choose to do so. But if you want to do other kinds of queries and other kinds of decision support that are not inherently spatial, and that's also what it's designed for. It's designed to be a simple spatial isn't special implementation. And that, of course, is my final point down there at the very bottom. It's just another data type. Now, we also wanted to provide room for our partners. Now, there are other things that we could have done. We could have added in, for instance, projection transformation support. Wouldn't have been very difficult to do. However, we have a lot of partners and very good partners who provide those kinds of services. Now, does that mean we won't do that in the future? Not at all. But it does mean that we think very carefully about how we play in this space to make sure that we make room for others so that we have a healthy ecosystem. We are also founded on strict adherence to spatial standards. In fact, some may argue, if you've actually worked with our product, that we were too strict in terms of adherence. We have two data types. One of our data types, which is the round Earth data type, geography, is so strict in its adherence to spatial standards that it will not allow you to put in non-valid data. Okay, well, that's pretty tight. We're going to loosen that up with the next version of SQL Server that comes out because we found that there's a lot of bad data out there. I knew that, but I was still surprised at the preponderance of it. SQL Server Spatial is designed to correctly handle geographic or round Earth data, and that's something that's very important to understand. It's very easy to do what we call coordinate system abuse. Taking latitude and longitude coordinates, pretending that they're actually rectilinear, and then manipulating, asking questions, querying across that data. We would prefer that you didn't do that. We can show you, in fact we will here in a little bit, about how you can abuse coordinate systems. And we will do a little coordinate system abuse as part of our demo here. All right. Often in Microsoft, in Redmond in particular, we are asked to give one slide that completely encapsulates our topic. And this is my one slide, of course split into four because you couldn't do it in one slide, right? So I'm not going to go into this in great detail here, but all of you should you'll be able to download a copy of this presentation and take a look. But these are kind of the standard precepts. I do want to point one thing out, however. We have a redistributable spatial library. Spatial is implemented as a CLR UDT. And as such, we have an assembly that's associated with that, a DLL. We license that separately and freely. And where do we find it? We find it on the SQL Server Feature Packs page. And it's listed as the SQL Server CLR types assembly. That assembly may be used by you or your partners or customers in order to provide the same functionality that we surface in SQL Server is now available in that library. Bug for bug, if there were any bugs. Feature for feature, and there's lots of features. So that if you wish to do a point and polygon, or if you wish to serialize or deserialize spatial objects anywhere in the processing chain, from the middle tier to the client, you can use that library to do so. It's an extremely powerful thing. So I want you to remember that, and remember the fact that it is freely redistributable. And here are the spatial primitives. I mean, for how many of you, just so I can get a little bit of a feeling, is this new stuff? Everybody who hasn't seen this before or something of this nature? Okay, so we've got a pretty good section of the audience here. These are the standard spatial data primitives. We have points. Everybody knows what that is. X and Y, latitude and longitude. We have homogeneous collections of them called multi-points. We have line strings, XY, 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 or homogeneous collections of them. We have polygons. What's a polygon? It's an area demarcation in which the beginning set of XY, XY, XYs is the same as the ending set. Well, you may have polygon holes on the interior of that. How many people know how many holes do we allow in a single spatial object in SQL Server? 65,000, just so you can all remember that. That's a lot. Also, polygons may be very large. In fact, all spatial objects may be very large. Does anybody know what the limit is in SQL Server in terms of how big a single spatial object can be? And remember, you can have 1,023 spatial objects per table, or actually per row in a table. Why not 1,024, which is actually SQL Server's table size limit, without going to sparse columns? It is because we need to have a primary key. So how big can an individual spatial object be? Any guesses? How big? 4? No, half that. 2. And that translates to approximately 125 to 150,000 vertices per spatial object. That's a lot. In fact, I don't know of a machine around that can easily digest that. There are a few out there, but if you had 1,023 of these per row, each at 2 gigabytes, well, you'd need more computing machinery, I think, than exists in the United States, Australia and New Zealand combined. So the limits are very high, is what the bottom line is here. You may also have multi-polygons, and you may have geometry collections, which are heterogeneous collections of all of the previous classes of data. Heterogeneous classes like geometry collections are not very common. We can create them from our spatial methods, but in general, we don't run into them. Just to recap here, spatial objects are features on maps. This is just an example here of what you might, how you might interpret information. A map is typically stylized, but the underlying primitives, again, are typically polygons, points, and line strings. Raster data versus vector data. Very important here. SQL Server 2008 Spatial is a vector implementation. It's 2D also. This is 2D data. Does that mean we cannot handle 3D? No. It just means that we haven't surfaced it. Our object model actually is XY, or latitude, longitude, Z, and M for measure. We also have an SRID, spatial reference ID, associated with every single object. So Why haven't we surfaced anything beyond this? Simply because we're so young in the game here. Our next version will surface some more functionality coming out, but we remain primarily a two-dimensional vector data implementation. Raster data that you see here, and we're just using an example, points, lines, and polygons again, are just picture elements, much like an image. The vector data is circumscribed in black there just to give you an idea of how they might relate to each other. Will we someday do raster? Very possibly, but we would like to hear from you and others as to what you expect out of that, because we have a lot of capabilities that are built into the SQL Server standard types to begin with. Raster and vector data integration. Can we actually use raster data and vector data? Well, the raster data here is a Bing Maps image in the background, actually multiple Bing Maps images. Bing Maps, of course, is made up of 256 by 256 pixel tiles. If you've ever had a slow connection with Bing Maps, you've noticed that blocks of tiles come in. And those are raster data. In this case, we have vector data in the form of census block group polygons draped on top of that, and that's what you see in the center in color. So let's talk a little bit about our data types. We have two data types: geography, that's round earth or geodetic data, latitude and longitude coordinates, and we have geometry, planar. What's the name of our state national coordinate system here in New Zealand, Matty? It's a transverse Mercator. So a transverse Mercator is a way of taking a round earth and flattening it. And for New Zealand, there are specific parameters that are designed to minimize distortion. But anytime you have to flatten your map, take your round earth and make it flat, you will have different kinds of distortions. So typically, national grids or geometry data types tend to try and minimize that, but you will always find some. General rule of thumb is, if you don't know why you need to have a flat earth or a planar projection system, then you don't. If you know why you need it, and there are often cases for it, then you do. Cadastral systems, very typically. My guess is LINS probably requires a geometry type.
It's a mandate in New Zealand.
Exactly, and we have the same mandate in the United States. We have something called state plane coordinate systems. California, for instance, is divided up into 6 different state plane zones, and that division is done to minimize distortion. But it also means that when you need to cross boundaries, and we all know that project areas tend to happen at the corners of 4 map sheets or at 4 boundaries, you often have to cross these. You do not need to worry about that when you use the geography type, because it treats the Earth as a single unit sphere. There are no edges. There's no top, no bottom, no right, no left. Or as I say, there be no dragons at the edges. Remember the old map sheets. Okay, so the geography type is not fully standardized. Why? There is no set of standards that fully addresses the capabilities of the round earth type, surprisingly enough. Even the Open Geospatial Consortium, note GEO there, right, is actually a flat earth society. Many of our vendors, well-known vendors, also believe the earth is flat still primarily. So I'm on a little bit of a jihad to try and make sure that people understand that, number one, spatial isn't special, it's just another data type, and that the earth is round. Our geometry type, on the other hand, is fully compliant, of course, with these flat earth standards. Oh, pardon me. Okay, voice is coming and going here, but it's hanging in there. Okay, now we also, in order to manipulate spatial, we need methods or functions. In our case, we have implemented a method interface. We have a very, very rich collection of these. One's for retrieving properties of objects, constructing objects. We also can return 3 standard compilations. WKT, well-known text. WKB, well-known binary. and GML, Geographic Markup Language. All of these are standard structures. We also, and I'll show you this in a little bit today, is we can take industry standard formats like shape files. Potentially, I'm going to show you some alpha software here in a little bit to actually ingest something like a shape file, which if you haven't run across them yet, you will if you get involved in Spatial. We also have two indexes, an index for geometry and an index for geography. Okay, so let's talk a little bit about planar versus round Earth. On the left-hand side, you'll notice over here a planar representation of the Earth. And because there are edges, if we were to ask the simple question, what is the distance from Anchorage to Tokyo, the red line would be our answer. And within that domain, in that context, that's true. But it isn't correct, because we know that we really want the shortest distance here, pardon me, that it's really on a flat Earth, it doesn't have the capabilities of giving us the correct answer. We cannot go across those planar edges. On a round Earth, we can. And so we get the correct answer. Now, this is an interesting one. Something like Google Earth, probably is anybody in the room not played with Google Earth? Did I see anybody? I'm hoping everybody's played with it. And we all primarily think of it, and I did up until rather recently, as a round Earth implementation. Why is it a round Earth implementation? Let me shell out here. And here we go. Is unable to connect to the servers. You know why? I need a network connection. And if I plug in one of these plethora of cables here, I get a network connection. Isn't that amazing? Let's just see here if we're going to have it work. That looks good. So look at this. I mean, we can basically, there are no edges, right? We can go around the Earth. We can circle around the Earth. So let's go over here right now to the equator and the international date line, the plus or minus 180th meridian. And let's actually, and I'm not going to actually draw it because I've done it earlier and saved it. I'm going to draw a polygon, roughly a box, that crosses the equator and the international date line. And what I expect to have is a filled polygon of exactly that, an area just in that small region. Does anybody know what I'm going to get? Yep, a band around the Earth. And that's because Google Earth is a flat Earth implementation. Okay, and there you go. Look at that. It gave me exactly opposite of what I expected. So how do they do this? Well, this round globe that you see here is actually an orthographic projection, and every time they move this flat Earth orthographic projection, they reproject, and they reproject. It's extremely clever, but it indicates that they do not have a full grasp on, again, the fact that the Earth is round. So what can we do here? So I'm going to move out here, if I can figure out where it is, to SQL Server Management Studio, and with a little luck here, I'm going to replicate what Google Earth did accidentally. So we're going to do a flat Earth international dateline box. And what have I done here? I have constructed a geometry here using the method ST geom from text. Very important here. Remember, this is .NET in the database server, right? So I'm case sensitive. So ST, spatial temporo, that's the industry standard prefix. That lets us know that I'm using an industry standard method here. Geom from text. And then I'm using well-known text in here. Remember we talked about WKT a few minutes ago? I have, quote, polygon, and you can see I've actually constructed a string of coordinates. And then at the very end, I've got a 0, which says there is no associated coordinate system with this. And with that, I can actually construct a box, and I'm going to union it with data from the for the rest of the Earth. And we're going to take a look at that little box here. And there's my results here. Notice, no column name, that's my geometry data that's being returned. And I can hit spatial results. And look at that. I have replicated what Google Earth had done. I got that band, right? Because in the geometry type, flat Earth type, it has no other way to reconcile that but to give me the wrong answer, or what it thinks is the correct answer. Now let's do exactly that same query, except this time I'm going to construct a geography object. And I'm using the same st from text command. And I'm using the same set of coordinates. This time, however, I'm using 4326. That is special spatial speak. And remember, we're trying to make spatial, not special. But one of the things is coordinate systems are like collations. They're like languages. We have to make sure here that we're all talking in English. Or in this case, we're all talking WGS84. This is the datum, the ellipsoid that GPS units speak. So this is a very common way to find our data. 4326 is shorthand. It's actually EPSG, the European Oil and Gas Consortium's standard set of nomenclature. It's a primary key. It's a magical number that we all know means WGS84. And that's one of the little spatial is special pieces that we need to understand. And here I'm going to do the same query. Well, if I can stop my mouse. Okay, I didn't make my query go far enough. There we go. And here we are, same result sets. But look at it this time. This time we have a little box on the left and a little box on the right. Put them together. You see that at the international date line, which is the right and left edges? And we see the little box now that's been cut in half. That's the correct representation in this particular flat Earth display. So this is a display here. This is Management Studio. Management Studio understands the difference between a flat Earth and a round Earth, even when it's projecting it into a flat Earth display, because that's the only way we can look at data, is when it's been projected into a flat Earth display. Okay, so let's, with that, jump back in to our presentation. Okay. So, needless to say, you can probably also do a little experiment of your own on something like EOSRI's ArcGIS Explorer. Try it and see what you get. Okay, let's talk a little bit about spatial objects here. This is an interesting one. This is from CSIRO. This is Australia. This is what? What kind of data type does this represent? Is it a point? No. Is it a line string? No. Is it a polygon? No. It's a multi-polygon. Why is it a multi-polygon? Because you notice over here, especially in that upper right-hand one off of Cape Tribulation, though I got some flack from the Aussies that wasn't Cape Tribulation, and then somebody came back and said it absolutely was, and they ended up going off and having a fight outside the room all by themselves. But I believe that is Cape Tribulation up there. And the Aussies tend to want to go fight a lot, don't they? Go figure. So you notice all those islands out there, and of course along the coast of the Gold Coast, Brisbane and so on, and Cairns. Notice I pronounced that correctly, Cairns. They beat that into me too. I still say it should be Cairns, but they want to insist on Cairns. But I can do that. So what we've done here is we've given increasingly greater resolutions into the data all the way down to the left-hand image, in which you can see, if you have better eyesight than I do, all the little dots. It's point to point. It's etch-a-sketch. That is how spatial data is actually put together and constructed. This particular object, this is one spatial object, mind you now. It's not multiple. This one spatial object is about 1.7 million vertices, easily managed and manipulated inside of SQL Server. So let's talk about complex geometry. This particular piece of geometry is a soil polygon from Upper British Columbia for part of the TRIM project. This has got 6,147 holes inside this polygon. Can SQL Server manipulate something this complex? Absolutely. This is a 2-kilometer buffer around that, including the holes. So this gives you an example. We can handle large data, we can handle complex data, and we can handle large quantities of data. This is the European Environmental Agency's Corine 2006 data, which is land cover for all of Europe. And what European Environmental Agency has done under the EU auspices has been to coordinate the standard structure of environmental data, in this particular case, across country borders. And they've produced these large, continuous, seamless data sets. These are almost like puzzle pieces, right, of data that has been fitted all together into this continuous fabric. And all of this data, incidentally, I've also loaded up into SQL Azure. It's a very interesting data set, but it does give you an idea that large quantities of data can be manipulated and handled easily in SQL Server. Again, we've actually already shown you this, but Management Studio handles SQL spatial data very nicely. And if we had multiple spatial columns down there, we could show them. Now, something I want to emphasize to you, because people are, even knowledgeable people in the field, not Maddie, but everybody else, knows that, or it doesn't understand that you can have a mixture of round earth and flat earth data in the same table, right? You can have a column of geometry next to a column of geography. Well, you say, why would you want to do that? Well, there are many reasons. I'm not going to go into all of them because I'd lose my voice even more than I already am. But you could, for instance, have two different vendors or data. For instance, you could have the way ESRI stores data, you could have it the way MapInfo does, and you could put a trigger between the two and have it automatically update the data between the two. And there are lots of other reasons why you might want to do this. Thank you. Okay, we'll skip Management Studio since we've already looked at it a bit. Let's go into indexing for a second. I'm doing pretty good. Could be better, however. Okay. What we have implemented is an adaptive multi-level grid index. In essence, a quad tree. And what do? We tessellate space. If I really lose it, Maddie, I'll have to have you come up and finish it. Okay, that's better. And in this case, we have a polygon with a hole in it, and we have 4 different levels of tessellation. It's a 4-level grid file. I'll give you a little hint as we go along here. I'm just going to do the tessellation. The adaptive portion is where we throw out or reject different grid cells. The fewer grid cells, the better. Then the adaptive portion allows us to fine-tune this as we go and we tessellate at different levels. And you notice that we've removed a grid cell now out of the middle of the polygon where there's a hole. So it's an optimized indexed. Okay, and this gives you an example of what the final optimized adaptive tessellation might look like. It's all done on a B tree also. Here's a little insight into the next level of SQL Server coming out, which will be out in a bit. I'm not going to give any hard line, though everybody would love me to. And I'll just give you one little tempting tidbit. We have a really adaptive self-tuning index coming out for the next version. And this has 4 levels of depth. The next one has 8. This has never been done before in the industry. Performance can be outstanding for the right scenarios. And more importantly, it reduces some of the tuning parameters. And of course, tuning parameters are the anathema, that's hard to say with no voice, of SQL Server. We like to have a knobless system. The next one is going to remove a lot of the tuning requirements while giving even greater performance. Okay, so spatial index, adaptive multi-level, 4 levels, customizable ranges, subdivisions. We can change the number of cells per object. We've got enough tuning parameters in there to confuse even the development team. So it's a hard thing to tune. I will show you a tool today that we have, again under Alpha, that makes a stab at actually trying to profile the data and actually create the index on the fly correctly for you. We've already talked about some facts with SQL Server. We'll just go through a few additional ones. You may have up to 249 spatial indexes per column. And remember, you could also have 1023 columns per table. You could have 1023 times 249 spatial index if you so desired. And there are good reasons why you may want to do this. Not that many, by the way, why you may want to have multiple spatial indexes. One thing I do want to mention, polygons in general, in the geometry type, we don't care which direction they're oriented, clockwise or counterclockwise. On the ellipsoid, when the Earth is a single entity, a closed surface, there is no such thing as right hand and left hand, and we can prove that, or excuse me, counterclockwise and clockwise. But there is a left-hand rule and a right-hand rule. Oracle, DB2 geodetic, Informix geodetic, and ourselves for our round Earth type adhere to something we call the left-hand rule. How many people are familiar with this left-hand rule here? That's actually right-hand, right? This left-hand rule here. This is the one they use in physics, right? We don't use that one. So, more correctly, this would be called the left foot rule. So that means that as you are walking along the outside of a polygon, right, if you're with your right leg, if your left foot were on the inside of this as you walked along it, you're going the direction that we would normally circumscribe a polygon in. Direction's important. Why is direction important? Imagine over Auckland if we define a 1 meter polygon that was designed to represent, let's say, a manhole cover. That's fine. Now let's reverse the coordinates the other direction. What do we have? We have the rest of the globe except for that 1 meter, right? That's why the coordinate order is important. Oracle uses that in Oracle Spatial for all of its coordinate systems, be they geography or geometry types. We don't. With our flat Earth type, we can figure that out, so we don't make that a requirement. For our geography type, we can't figure out what you want. So we force you to do this particular ordering. Beware, shapefiles in particular like to order things the opposite direction. So we have tools to help handle this for you, but it is important. And this is, again, a little part of where spatial is special. So we need to know a little bit of the details here. Okay. Here's an example of some spatial queries where actually I'm not going to concentrate on this because I'm going to jump in and do some spatial queries here in a second. Just the red things are spatial queries. We didn't have very many aggregates and interesting things. Why didn't we have aggregates and a few other additional methods? Because they weren't specified in the standard, and we almost ran out of time on last release getting everything in. So what did we do? We have a Codeplex site. So if you go to www.codeplex.com, and I have a slide at the very end of this with resources, and it's mentioned there, the development team has put together a new assembly with a series of missing tools. You may register that with a database instance, and you now have access. They're not with a method interface. It's now a function interface, but we have things like geometry envelope aggregates. So in this case, this is all of Africa, and we're asking for the bounding rectangle, and this is in the geometry type, the bounding rectangle that encompasses all of Africa, which includes the extremity islands out there, and that light blue polygon is the single aggregate of all of the extents of the objects in Africa. Here's one, a geography union aggregate, and it looks like I misspelled geography. Caught that, that's great. Here's all the provinces of France, and if they're unioned together into a geography union aggregate, you have just the country of France. Very important, powerful thing. Next version of SQL Server, these are all going to be incorporated as standard methods. R2 of SQL Server, it's our current generation, not our next generation. Next generation is what I've been giving you a few little details about here, some little tidbits. This is SQL Server Reporting Services, out now as R2. And with that, you can actually do spatial reports. And in fact, if you notice on the right, there's a Bing Maps raster background there. That's fully licensed. If you wish to use SQL Server with Bing there, it's fully licensed. You're welcome to do so. No need for an additional Bing license. Here's another example. In the Economist, there was a set of missile ranges coming out of Iran. I modeled that using the reporting services, and in this case I used a Bing Maps background, an image background, raster background, and I added an additional report showing the countries that are impacted here by doing certain spatial methods like intersection, and we came up with a population. And no, that's not the population that's underneath the rings. It should be, but it isn't, just so you don't catch me on that. There are other products out there that utilize all this. Here's an example of ESRI's product, Mapit. I'll just kind of leave it at that. Tomorrow I'm actually going to show a lot of products that actually work with SQL Azure. Anything that works with SQL Azure also typically works with SQL Server. So you'll need to come tomorrow to see some of the rest of them. And now I'm going to give a little series of demonstrations here in my remaining time. My voice is holding out, which is absolutely amazing. Okay, so what am I going to do first? I'm going to go into Management Studio. If I can find it. There it is. And we're going to go into, I've already preloaded some tables. This is from a small county in California called Kern County. And I have a bunch of data that I'm going to work with in SQL Server. So I have city limits and county boundaries. I have a set of fire station points, water course lines, water body polygons, and I'm going to union all of them together so I can display them. And oh, look at that, I've got an error. I'm missing one of my database tables. Well, I've got a shapefile for this. How can I get this in? And this, incidentally, is a common question. How do I get data in? Shapefiles are a common form of data, and what you're going to see next is our new alpha. It's not yet out for public consumption. Shapefile import tool. Now, what does this do? This allows us to go over and identify, browse for data to import. And you notice I've already downloaded a file, firestation.shp. I do want to tell everybody that a shapefile, while it sounds singular, is actually plural. There are many components to a shapefile. .shp is the geographic component, but the attribute component that has all of the different columns of related data with it is actually in a .dbf file. The map projection itself may be in a .prj file, and there may be an index with that, a .shx. In other words, it's a collection of files really that should be a shapefiles, but it isn't. And so typically we keep these in folders with the name of the shapefiles prefix there. So with that, though, we've got a shapefile identified. We're going to allow nulls. We're going to note, create, and optimize spatial index. It's automatically identified from the shapefile what the correct SRID is, trying to help you out here. And it notices that it is a geography type. You could push this into geometry, but it is proper to push this into geography because it is latitude and longitude data. Here are all the data columns. Notice that we don't have anything that was easily identified as a primary key, so we have the ability to go through and add a new identity column. In this case, we're going to call it ID. We're going to make it the primary key. We will identify our target database. Over here, a table name will be Fire Stations, and we will use SQL Server authentication. We could also use Windows authentication. We have a few other options over here, but let's go ahead and execute that. And with that, we've just loaded up the fire stations. And now if I come back here and re-execute that query, it works. Miracle of miracles. Better than my voice. Okay, and so there's the data. We can see some streams. We can see some, there were some water bodies up here. Those irregular polygons are city boundaries. And importantly, one of the limitations of SQL Server Management Studio's visual representation, and remember, it's supposed to be a helper for the DBA. I've just issued a series of queries. I can't look at that geometry gobbledygook, because if you look at it, it looks like hex, because it is. So this is a much more cogent way of looking at the data. Interestingly enough, SQL Server is the only database that provides out of the box in its Management Studio-like tool a spatial representation. So what happened to all the rest of us? When we did this prior, we never thought about it for some reason. I have no idea why. All I can say is this was sort of a revelation. We got it in at the very last minute in SQL Server because we had to. This is just too good to miss. It isn't a perfect tool, however. One of the problems is if you do point data, for instance, I'm going to come back here, modify this, and notice I have an ST buffer here, right? And a buffer is a widening of the object. In this case, I've widened it by 1 kilometer. I'm going to go take that out, and I'm going to rerun this query. And when I rerun this query, you'll see one of the apparent limitations, and you'll be right, of SQL Server in Management Studio. What happened to all those points? Basically, they're like fly specks. They're basically a single pixel displayed. Why? Because it's a whole nother interface to try and provide, symbology support now. What happens here, it just kind of keeps going on and on and on. Where do you stop? Now you need a full-blown editor to be able to provide symbology. So what we do with points is we tend to buffer them. And with that buffering, we can enlarge them to make them visible. Okay, again, spatial isn't special, but you need to know a few tricks. Okay, so we've got the data in there. Let's go ahead and query the data a little bit. So let's take a look at the fire stations relative to the city limits. Okay, there's the query executed. And now we can hopefully zoom in a bit here just to show you. So we've got these fire station points located all over the place. One of the things we're going to want to do is, what if we wanted to ask the question, show me all of the fire stations that fall within city limits of any of the set of polygons, which are the city limits polygons. What would we do in relational data terms? What would that be called? A join, right? So can we do joins in spatial? Absolutely. So how might we do a join? So let's go down here and take a look. Let me see if I can enlarge this a bit. But basically, we're going to select a few columns to put out. We're going to produce the geography column here with a buffer for around the points. We're going to get the station names from fire stations. But note down here, we're going to join. I'm going to actually change this because of the display resolution. We're going to join on city limits using an intersects method. So we're going to intersect B geography with A geography where it equals 1. It's a Boolean, right? So where true, where intersections are true, we're going to do that join. And then I'm going to union that display back again with the city limits. So notice what Bakersfield kind of looks like in the middle down here right now. That's that kind of light blue polygon with the majority of fire stations in it. We're going to execute that. And now, when we zoom in, notice we've just got fire stations that fall within city limits. Okay, so there's a join. So, spatial isn't special. Spatial is just another standard SQL type. We can do joins and all kinds of cool things. Now, what if we want to do some other specialty stuff? In this case, we're going to intersect. We're going to find just those fire stations that intersect the city of Bakersfield. In this case, Bakersfield was ID number 38. So I created an object directly from that query. And I'm going to now get just those fire stations that intersect the city of Bakersfield. But what if I want to do some other interesting queries? For instance, I want to buffer Bakersfield, the city, that polygon, by 4 kilometers, and then I want to see how many fire stations fall in that. How would I do that? Well, I could come over here and I could put a buffer of 4 kilometers around that. And you notice I also have another command over here, spatial command. This is a generalization command called reduce. It uses the Douglas-Poiker algorithm for anybody who's interested. It keeps the correct shape of objects, but it reduces the complexity in terms of the number of vertices. Why are we doing that? In SQL Server, it works fine. But tomorrow, as we'll see when we go into SQL Azure, you're asking it to do a much more complicated calculation. So we want to simplify the apparent complexity of the edge without compromising its shape. Because a buffer operation is, in any respect, a generalizing operation to boot. So let's take a look at what we do here when we execute that command. Okay, buffer is complete. Well, that's because I didn't, what didn't I do here? I didn't get the rest of the, got too excited. Okay, so now we've created a super object, right? We've created the city of Bakersfield now enlarged, buffered by 4 kilometers, and we've intersected that against that set of fire stations. Well, what if we wanted a zone of 4K around there? How would we do that? Well, we've got a method for that, and it's called ST_difference. ST_difference takes the difference between 2 spatial objects, subtracts the 2 of them. So let's go ahead and do that and see what we get. So here's that ST_difference here. We've computed the buffer above the 4K buffer right here. We've created the city of Bakersfield polygon right here. So that's the variable at B, and then the variable at C. We're subtracting the 2 of them with ST_difference, and we will get to see the results of that. We're going to intersect all the fire stations with that. And there you go. We produce now a zone, and we've intersected those fire stations. So this gives us a little bit of an idea of how we can go through and work with spatial data. Let's jump back to the presentation. Working with data. And so let's chat here in just a few remaining moments. We have a spatial roadmap ahead. What are we going to do? We've already heard we're going to give you some better tooling in terms of indexing, easier and faster indexing. We're going to improve our geography type, our round earth type usability. We're very, very particular about the data that goes into it now. There is something called make valid we can use on geography. You can take spaghetti, all kinds of mixed up data, shove it into the geometry type, and then run this magical command called make valid. Everybody loves that particular method. Can't do that method on geography, but we will be able to do that in the future coming up in the next version. So you have a fighting chance of getting bad data in there, investigating that bad data, and fixing that bad data. We're going to provide fast nearest neighbor computation for you using standard top blah, 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 order by syntax. Very straightforward stuff. No fancy nearest neighbor command, but it's a very usable tool. We are improving client-side connectivity in a number of areas. And then, of course, spatial aggregates, and we're going to bring out one new spatial object type, which I'm not going to share with you yet, but it's one that's often asked for. Spatial data tooling. You saw some of the tooling here just a second ago. We have things like an NMEA import tool. How many people know what NMEA is? Pretty good. It is National Marine Environmental Help me. NMEA, National Marine Electronics Association. And it is the standard specifier for GPS output. So an NMEA file typically comes out of GPS. So we're going to provide a standard way of getting GPS data into SQL Server, shapefile data into SQL Server, potentially geo-encoded imagery like that you take with an iPhone, an HTC phone, a GPS-equipped Nikon, a Ricoh. All of those can take GPS-encoded digital images. We're going to provide a tool to get that in, and we're looking to provide one more tool here. Let me see if I can go find it, because I think you'll like it. Where did I put that? Oh, I know where I put it. I put it right here. And this is the Spatial Explorer. The Spatial Explorer is another visualization tool. And this visualization tool is data-driven. Every select statement is another layer, in essence. And so this is data here, and actually I'll run this against SQL Server. This is NavTech data, and if it's interesting is we will provide a number of different backdrops so that you can look at this in Bing Maps. You'll be able to look at this in OpenStreetMap. Here's a number of different renditions in OpenStreetMap, including ESRI's World Street Map from ArcGIS.com. So the idea is that you're going to be able to see your data presented on top of a variety of different backdrops. We've also got it so that when you click on a particular object, it will highlight it in the table below. So we've tried to provide yet another piece of a little bit more sophisticated tooling. What we're looking to do is provide all these tools at no charge. Just asking you to register. So this is some of the things. This is a sneak preview here. And if you see me around later on and I still have a voice, tell me how you like them. If these look like things that you're interested in. What we want to do is try and capture the kind of the sizes and the interest of the SQL Server audience out there. So that's a little bit there, ending on the tooling. Let's drop back to the presentation. Where am I? And what I wanted to do here is just kind of wrap up with the SQL Server spatial resources. This is a good compendium of information here that if you're interested in spatial, you should familiarize yourselves with. There's blogs out there. The SQL Server Spatial Forum is very active. It's the third most active forum in SQL Server. Lots of interesting stuff. You can learn a huge amount by looking at the questions that are asked by others and the answers that are given. There's a couple of good books, including a chapter that Isaac and I wrote in Inside SQL Server 2008, T-SQL Programming. And importantly, there are specifications here for our data, including our serialization format. We're not hiding anything. We show you exactly how that disk is serialized, or data is serialized on disk, if you want to do something fancy yourself. And we also, with our namespaces down here, documentation, show you how the library itself is constructed. And the examples of that are all found on our CodePlex site. So I would encourage you to look at this, review it. There is a wealth of information here. With that, we've got about 5 minutes left. I want to encourage you to fill out your evaluation forms. And yes, you can say the speaker should be able to talk better than this. I really apologize for this, but I'll tell you, it's a lot better than it was 24 hours ago. I didn't think I was going to even be able to give this session. So I'm hoping I have not used up all of my voice so that I can also give the SQL Azure session tomorrow on Spatial. So with that, I'll take any questions, and thank you all very much. So who has some questions? Do I see one? Oh, yes.
I could be wrong, but am I correct in the understanding that you can have in each row a different, I'm assuming just one spatial column, a different projection or geography per row?
So yes. So let me rephrase that. Can we have more than one SR ID or spatial reference ID for a given row? And the answer is yes.
Why?
Because we believe that the spatial coordinate system, its language, its collation, should be associated with the object, right? And how would you control that? Because typically, because what you're leading to is, in general, we don't want to have multiple spatial references in a given column of any type. Much like you wouldn't want to have text, right, with English in one row and French in the next row with the same column. So what do we do in SQL, standard SQL syntax, for keeping it to be a homogeneous SRID? We use a constraint, right? So you set a constraint using the ST SRID method. So, but when you export data, what often happens in spatial is that when data gets removed from the system, it loses its knowledge about what language it's in. And that is the death of spatial data. The minute data gets feral without knowing what its language is, its coordinate system, we really can't, as spatial practitioners, use it. So we believe that the SRID, the spatial language, the projection, is an inalienable part of data. Okay? Is it a perfect solution? No. So it's, again, a little piece that spatial, it's a little special here. You may accidentally or intentionally put in multiple SRIDs in there for a given column. In general, you don't want to do that. What happens if you have data that you're joining that has different SRIDs? You get a null result, right? It's a no-op in essence. So it is important that you understand that you want to normalize all your data to the same SRID. Use your standard SQL tooling, like issuing constraints, in order to guarantee that you have in your database exactly what you expect in your database. But very good point, good catch. Any other questions? Yes, sir.
Getting like I'm a spatial virgin, getting actual databases of things like the spatial data of postcodes.
Of what?
Postcodes and things like that, like in Australia or New Zealand, you've got postcodes.
Yes.
Right, so that you know, and the spatial data on like like we've got customer in such and such a street somewhere, actually being able to relate it to the maps and things like that. How do we actually go about doing that?
So the question is, we've got a great database here that has a huge amount of capabilities. Where's the data? You know, how do I get the data in? And that is an oft-asked question. And that's one reason we're putting that tooling out there, is to make it one step easier. But it doesn't solve the problem of where is my data. Once we've found your data, we can get it in. There are a variety of ways to do this. There are commercial vendors. So, for instance, that last shot that you had of that nice, red dots all over Auckland, that is data from Navtech. And Navtech is the world's largest data provider. There are other data providers out there, and there's also a wealth of spatial data that is generally available. We do find, however, the United States leads the globe in terms of free data. Data escaped out to the public years ago, typically with U.S. Census data, and we have a tradition in the States of making available very sophisticated data for free. It isn't necessarily the case when we come down here or to Australia. So one of the things that we're going to attempt to do for you is to produce some sample data sets that put together all of the commonly found public data. So for instance, for my book chapter, I produced something called Sample USA, which was several gigabytes of standard US data. We may do the same over here for a Sample NZ and a Sample Oz databases to help you out, because this is actually proven to be a strong impediment for people who aren't new and used to the business. So it's an excellent question. It's an oft-asked question, and we will try and provide some sort of response to it. But you do have firms within the local area, Wellington and Auckland, that can help you out greatly also in terms of identifying these things. But shapefiles are the common form, and if you're pretty good with Google and Bing, you can go through and find a plethora of information out there in shapefile format and in other formats. So, but good question. Any other questions out here? Yes, sir.
Can you do spatial from SSIS, like process spatial data inside?
Great question. Can you do spatial data processing inside SSIS? And furthermore, how come SSIS doesn't have spatial support? So, what I'd like all of you to do is go to connect.microsoft.com and say, why doesn't SSIS have spatial support? But it's not going to change anytime soon because the SSIS folks tell us they've got more important things to do, and I have no doubt that there are more important things than spatial, though I can't think of a single one. So what if we want to use spatial within SSIS? Is there a choice? Can we do anything about that? And the answer is sure. You can use something called Feature Manipulation Engine, FME, from Safe Software, www.safe, just like you think it's spelled, .com. Small company in Surrey, British Columbia, and they produce the gold standard of spatial ETL. And, importantly, it works as an add-in, an extension of SSIS. 350 different transforms, including all the projection transformations that we don't ship, and 225 spatial format support. Just a monster, but it costs a lot of money. In many instances, it costs more than the SQL Server instance that you're running. So what have we done for you? We've done something very nice for you. We have a new version that we requested from SAFE. It's called the SQL Server Spatial Data Loader Edition, and it costs $500 US. It's the bargain of a lifetime, and it works inside of SSIS. So there is your SSIS solution. We couldn't build it, but we got the industry gold standard to build it and to price it right. It basically does data loading from a limited set of things, including shapefiles into SQL Server, and it provides the all-important spatial and coordinate system transformation support so that you don't end up with multiple SRIDs in your column. That was good. I kind of tied it all in together. Okay, more questions? Yep, yes, sir.
Best thing with coordinates is to have on-the-fly projection rather than say only store your latitude, longitude data in the database. That's the advantage of having projections built into the engine.
So the question is, in essence, why don't you have coordinate system transformation support built into the engine? And I can tell you why. Because when we spec'd our product, we looked at what it takes to actually maintain coordinate system and projection, the algorithms. And they are a dodgy set of code out there. You know, there's an awful... ESRI, to give you an example, the world's largest geospatial company, has a team that is approaching double the size of the SQL Server spatial team just to support the coordinate system and datum transformation code. Okay? We didn't want to do that. Furthermore, there are all kinds of other good projects out there like Proj4, which is a public domain coordinate system and datum transformation set of software, a library. So we've been thinking maybe what we need to do is provide a framework so that you can do exactly what you're looking for, but you can insert your favorite projection transformation engine. Because I'll be blunt, I have limited resources. I don't want to spend them on that dodgy code. And additionally, I will say this. I want to make a strong emphasis here. If you don't need to use the geometry data type, use the geography data type. It is a true geo data type. If you can avoid, and if you can manage using something like Safe Software and other ETL processes, get your data all normalized into the same coordinate system. Don't put it in there in English and French and Scottish and Welsh and expect to be able to do performant queries across all these different coordinate systems. Yes, you can do all kinds of cute pet tricks in the database server, but you really don't want to. What's of the greatest importance? Performance. And what's going to kill performance? Going through and doing all kinds of transformations where you don't have to. That said, there are legitimate reasons to be able to do just what that gentleman asked in the database server. So we are considering it, we're looking at it, but you know, given my response here is that it's not high on our priority list at the moment. But you could do that yourself, and if you want to see an example of how we've approached it one way, look at our Codeplex site. Again, that's on this resources page here. And we actually provide the source code for doing a few simple forward and inverse projection transformations there for you. Any additional questions? Yes, sir.
Sorry, you mentioned you had another session tomorrow. What time?
That session, I believe, is like 11:30, 11:25 in the morning. Just enough time for me to recharge with a few cups of hot tea, my speaking voice. And we will continue this discussion and conversation and adjust it up into the cloud. SQL Azure. Good. Thank you all very much. And if you see me, please harass me and corner me in the halls, and because I love to talk about spatial. Just don't talk about it too much so I can't give my session tomorrow.
Hello.